Hello, calculus friends. Now we're doing section 2.6 today, and this is where things really start to pick up speed. This is where it gets exciting. I'm happy about this one. This is all about the magic D word that we're going to learn today. So that's going to be new, but rates of change we already know from previous sections, so we're going to sort of link those together today. Okay, we started the whole year asking the question on a graph, if I have a curve like this and I want to find the slope of the tangent line to there, which we also said was the instantaneous change, right? And so what we did is we took that point and we kind of cheated by moving another point over there and making a secant slope and moving that point closer and closer and closer and closer and trying to find all these average velocities in the hopes of getting closer to the instantaneous velocity or instantaneous rate of change. So that's still our goal. We're still looking for that. And the way we did it is by taking all the slopes of the secant lines, which was finding the average. Okay, so the picture over here on the right-hand side is basically what we were doing before. If you're given A and another A value over here, which we can just call X, here are the corresponding Y values and Y values. Here over here is the rise or change in Y's. And over here is the run, or the change in x's. Okay, so we were using the slope formula to find the slope of the secant line, which was the average. And it was trying to get us closer and closer to this friend, the instantaneous. What's happening right there? Well, as we said, this instantaneous is the slope of the tangent line. Again, we couldn't find it before because it was only at one single point P right here. And we can't find the slope from one point. So as you can see here, we try to find the slope of the secant line. And we brought that Q point closer and closer to estimate what the slope of this red tangent line would be. What would that instantaneous change be? Well, we just came from a whole bunch of sections talking about this bad boy, right? So what if we took the limit of all of these secant slopes to try to approximate the tangent at P? Okay, well, we know how to do that because we've been doing limits for the past week or so. So here's what we've been doing before. This is the old way. This is M is slope of the line PQ. What's this? This was rise over run, right? This is the change in the Y values over the change in X values. And you can see the X's and the A's relate to the graph up here that I was marking up. So X and A and f of X and f of A. Okay, so that's rise over run. We've done this. Check. That's good. So why don't we take, here's the magic word, ready? Why don't we take the limit of all of those secant slopes as, now look what happens. In order to find the slope at this point P, going up here, it's like I need to bring the X value closer and closer and closer to A to find out what is the actual tangent, boom, at A. So look at how we write this. We say that's the limit as X approaches A of, well, this is just my secant formula, right? So I'm taking my secant formula, but now I'm using the magic word of limit. And that's going to hopefully find for us right here the tangent slope that we've been trying to do. Now, we can do this as long, as you see here, as long as the limit exists, we're totally allowed to do this. But from before, just in case the limit doesn't exist, we have other ways, right? We have algebra, we have rationalizing, and all that jazz. Okay, just a little bit of notation here, friends. When we say the slope of the tangent line, we're also saying that's the same thing as the slope of the curve on the graph. And that sounds a little weird, right? Because you can't really find the slope of a curve because a curve is, well, it's curvy, right? It's not a straight line, so we can't find the slope. But we're going to say when we draw that tangent line at that point right there, the slope of the tangent line is the same thing as saying the slope of the purple curve at that point. Okay, so they are interchangeable. You hear them both. We'll say, hey, what's the slope of the curve? You'll be like, oh, okay, what's the slope of the tangent line? That's basically what we mean. Okay, well, how are we going to do that? Well, let's try it. Let's try using our new limit formula here for number 1 and 2. So given our function, f of x is x squared, or y equals x squared, our typical parabola. For number 1, let's find the slope of the tangent line. We can do this now, yes, at our point P1, 1. Okay, ready? So we're basically going to do the limit as x approaches the point 1. Okay. So if I do that, I want to try to find, using the formula that we had before, f of x minus f of a over x minus a. Now, we need to talk about some of these letters, folks. The a's and the f of a's are the values that you're given. So can I relabel? This is p is really a comma f of a. Both, in fact, happen to be 1 and 1. That's just because of the point we picked. But x and y generally relate to a and f of a. X is a, and the y value is f of a. Okay, so let's plug that in. This is the limit as x approaches 1 of, well, f of x is just f of x. I'm not sure what that is yet. We'll come back to it. Minus, what's f of a? Oh, it's the y value, 1. And on the bottom, x is just x minus 1. But wait, don't we know what f of x is? Didn't they give that to us over here? Yeah, it's x squared. So why don't we write it like this? The limit as x approaches 1 of x squared minus the y value over x minus the x value. Yay! Okay, with every limit, folks, what should you do first? Plug it in. And if we try to plug it in, it does not work. So we have our algebra magic. Let's do some factoring. This is a nice, beautiful difference of squares. Once I do that, see ya. And left with, let's bring the limit back in to help us. The limit as x approaches 1 of what we left with. Just x plus 1. Okay, that's cool. Now can we plug it in? Oh, yeah, we can. And we get 1 plus 1 is 2. Good for you. Do you know what we just found? We found the slope of the tangent line, which we've never been able to do before. Hooray. And look at how we did it. We're basically sneaky. We're being sneaky. We used the secant slope formula, but we found the limit of it, which we've been doing for the past week or so. So we're taking the limit of all the secant slopes, and that gave us our tangent slope. All right. Part 1, check. Now, part 2 is very, very popular for the AP test. We're going to often need to find the equation of that tangent line. We found the slope, which is 2, but what's the actual equation of that tangent line? All right. Now, for the AP, big star here, friends. Whenever you need to find the slope of the tangent line, we're going to use the point slope formula, which is this, friend. Always, always, always. Not slope intercept, not standard form. We're going to always use point slope. The reason is it's very easy to plug in and simplify and just leave it. We don't have to mess with it at all. Well, let's do it. Okay. Well, the x1 and the y1 are the ones they gave you, or a and f of a, or, and here it was, 1 comma 1, right? So let's plug it in. The slope of my tangent line should be y minus the y value of p equals, what's the slope? Hey, we found it over here in part 1, right? That's 2. That's the slope of my tangent line. That's m times x minus the x value, or a, which is 1. Now, I'm really, really tempted to do algebra and be like, oh, okay, I'm going to maybe distribute and try to get point slope form. But no, don't, I mean slope intercept form. Don't do that. Don't do that. The AP is totally happy with this answer, unsimplified. Just leave it for that and walk away. All right, so point slope form we'll always use for tangent line equations, and we're going to put it in there and we're going to leave it. Wow, that's a big step, folks. Look what you did. You found the slope of the tangent line, and you found the actual equation of that tangent line. So what you did is, if this is your y equals x squared, and this is your point at 1 comma 1, you found the slope of this tangent line, which is 2. And then you actually found the equation of that tangent line, which is right down here. That's a huge step. Good for you guys. Let's try another example. Can you find for me the equation of the tangent line of this curve at my given point? So you see that's xy, or a, f of a with our formula. Now here's the thing. Notice how this question is different from the one before. Do you notice how it doesn't say part 1, doesn't say find the slope of the tangent line? But if you need the equation, you need the slope. So they're actually kind of inferring you have to find part 1 first. In order to find the equation of the tangent line, you need the slope. So really, we have to do part 1 first. Now, I'm going to set this one up. You're going to see the algebra here is kind of evil. And I'm going to show you that later we've got shortcuts. So for now, let's just set it up, see how evil it is, laugh at it, and then walk away. Okay, this is going to be the limit. So first we're going to find the slope, right? We're going to find the slope of the tangent line. This is the limit as x approaches my a value of, remember it's f of x, I'll just write it so we can remember, minus f of a over x minus a. Okay, limit. What's my f of x? Here you go. Let's plug them in. That's x plus 2 over x minus 1 minus f of a. Remember, that's the y value. That's here. Okay, that's the change in y's on top. On the bottom, we have the change in x's, which is just regular x, minus your a value is right here, the 2. Good. So you can see the algebra here is really tough because you're going to need to find a common denominator on top. Right now, even just looking at the limit, we can't plug it in, right? Which is why I'm jumping right away to the algebra. So you'd have to do a lot of algebra here. The good news is when we have a fraction like this, folks, we're going to have a better way of finding the equation of the tangent line in the slope. So for now, I'm going to walk away from that because we're not going to try these kind of problems until we've learned that shortcut. But the one thing I want you to practice, actually two things, is I want you to recognize that when you find the equation of the tangent line, you have to find the slope first, which is what we did in part 1. Okay, you have to use our new limit of the secant slopes to find the slope. And then I want you to also notice just practicing how to plug it into the formula using limits. Okay, so I'm okay to walk away from that if you're okay. Are you okay? I'm okay. Let's walk away. So that formula is great, but can I show you a more powerful one that we're going to use probably actually more often than that secant formula. All right, here's our diagram again, but look what I did. Instead of saying a and x, I'm going to say my x value is just some number a, and then the distance that I'm going to travel from that point to the next point is some value h. So this is almost like x sub 0 and x sub 1 in a way, because the distance I travel between those 2 points is h. Why? You'll see in a second. But now if those are my new x values, x0 and x1, look at what my new y values that correspond. That would be y1, right? That's f of a plus h. And over here, that is f of x0, because that's f of a. So that's basically almost like y0. Okay? So look at what our new rise, the change in y's. That's f of a plus h minus f of a. And look what our new change in x is, our new run. Well, this I need to see. This would be one of them, a plus h minus the other one. Wait, what's happening here? Oh, see ya. So our actual run or change in x's are just going to be a single letter h. Maybe that's why we changed our letters. Okay, so now look what happens. If I do my rise on top and my new run on the bottom, look at that formula. For those of you who took pre-calculus regular last year, you recognize this is what we call the difference quotient, right? Oh, yay, it's back. Okay, so right now this is still the slope of the secant line. How do I make it tangent? Boom! Let's put a limit on there. But look what our limit is. I want to bring x1 closer and closer and closer to x0 to make it a tangent line, not a secant. In order to bring it closer and closer and closer, what do I have to do with my h distance between them? It has to get smaller and smaller and smaller, meaning my h distance needs to get really, really close to 0. Now look at this formula. This is another formula for the tangent slope. The one before used the secant formula, and this is still kind of the secant formula, but this one's more popular because there's, well, first of all, the denominator looks a lot easier, and this comes from the difference quotient formula that we'll talk about later if you remember from last year. Okay, so this is equation number 2. Rise over run, but we're taking the limit. Shall we try it? Let's try it with this new formula and see, maybe one is easier than the other. Let's find the equation of the tangent line. And already, as soon as I say equation of the tangent line, you're already thinking, I have to find the slope first. I have to find the slope of the tangent line first, Mr. Brown. Okay, cool. Calm down. And here's my equation. Y equals 3x squared minus 2x plus 1. And here's my a and f of a, my x comma y, at the point, negative 1, 6. And that's our point P that we're always trying to get really, really close to, like you see up here in the diagram. That's the point I'm getting really close to. The Q value is the one that, remember, I'm trying to bring closer and closer and closer to the P. The P here stays solid. Okay, let's see if I can figure this out. Now I'm going to need probably a little extra room here. So let me go to another page and see if I can find some room. 3x squared minus 2x plus 1. All right. That's our f of x. And we were doing at the point. We said negative 1 comma 6. All right, Mr. Brown, let's do it. I'm ready. The p point here is negative 1 comma 6. Can we find the equation of the tangent line? So let's do the tangent slope first. That's going to be the limit. As now our new one says, as h goes to 0, the distance between the x's gets closer and closer to 0. So as h goes to 0 of, let me write it out first. This was f of a plus h minus f of a over h. That's our new formula that looks like the difference quotient. Okay. Well, here we do know what a is, so I could plug that in, right? Because a is here, negative 1. F of a here is 6, right? X and y. So let me plug that in. That becomes the lim as h goes to 0 of f of negative 1 plus h minus f of a. That's just the y value. That's 6. Well, that's not too bad. Over h. Okay. Well, before I figure out what the heck this guy is, let me just try it just to see. Can it work? Can I just plug in h equals 0 now? Oh, I can. Okay. Well, let's keep going with what we're doing. Maybe some algebra is going to help. All right. Let me bring this friend over for a second. Come here, buddy. I want to find for a sec, what is f of negative 1 plus h? What is that? Well, if here's our function, friends, I'm going to basically take negative 1 plus h, and I'm going to sub that in for every single x here, right? That's what that means. When you do f of something, f of 1, f of 2, f of 5, those numbers go in and substitute and replace the x's. So do you guys believe that f of negative 1 plus h would be 3 times negative 1 plus h squared minus 2 times negative 1 plus h plus 1, right? It's like I took the original f of x and I just substituted in the negative 1 plus h for all the x's. Okay, well, let's simplify that because we can do a little bit of foiling, a little bit of multiplying. This is 3 times. Okay, in your brain, you're thinking negative 1 plus h times negative 1 plus h, right? We can't distribute the 2. That's bad algebra. Okay, when I FOIL that, I should get 1 minus 2h plus h squared once you do all the hard work. I can actually go ahead and distribute this negative 2 into these friends here. That would be positive 2 minus 2h plus 1. How's your algebra doing here, friends? All right, distribute in. How about 3 minus 6h plus 3h squared, right? Multiply the 3 in. Plus 2 minus 2h plus 1. Okay, this is looking good. Now I'm just going to gather all my like terms together. I've got an h squared, so I've got 3 of them. In terms of my h's, I've got a minus 6h and a minus 2h. Me thinks that's minus 8h. Okay, how about any leftover numbers? I've got a 3, I've got a 2, I've got a 1. I say that's plus 6. Cool. So that's going to go back and substitute back into our limit formula up here, folks. So I still have to attach the negative 6 at the end. Okay, so let's start back over here. Whew, this is exhausting, right? I can't wait for the shortcuts coming soon to a theater near you. Limit as h goes to 0 of, well, now I'm going to plug this whole thing in for f of negative 1 plus h. That's 3h squared minus 8h plus 6. Okay, and the rest of that numerator is minus 6 from up here on the top right. Whole thing divided by h. Still can't plug in that limit, right? Well, let's just keep playing with the top here, folks. This is the limit as h goes to 0. Well, let's get rid of those parentheses. Release the parentheses. 3h squared minus 8h plus 6 minus 6 over h. Ooh, I see some canceling. Get the... Ah, nice. Okay, now leftovers. How about the lim as h goes to 0 of 3h squared minus 8h? Ooh, do you notice there's an h everywhere? I'm going to factor it out on the top and see what happens. Can you see, friends, how important your algebra needs to be? Oh my goodness. But bravo if you've made it so far here and you are not dead. Here comes the h's. See ya! Now that's really cool because remember the whole problem was I couldn't plug 0 in for h because that stupid denominator. But now he's going to be gone. Check this out. This is the lim as h goes to 0 of, look, 3h minus 8. Wow, that's pretty. Now can you plug h equals 0 in? Oh yeah, you can. Check this out. Now let's plug in h is 0. I got 3 times 0 minus 8. That's 0 minus 8. That's negative 8. Yay! What did you just find after all that? Do you even know what we were doing? I lost track. Oh, that's right. We were finding the slope. That's the slope of the tangent line. So no more. We don't have to find secant slopes and estimate like before. We can just go right for the jugular and use our brand new formula up here, friends, for slope. Awesome, 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 awesome. Okay, so the question was asking not just for the slope, but they want the equation of the tangent line. So, boy, we did a lot of work. That's great. If we want the equation of the tangent line, remember we're going to use our point slope formula. Y minus y1 equals slope x minus x1. Let's always use this. We never need slope intercept. Always, always, always. Okay, ready? Let's plug it in. We get y minus, well, what was your y value? Do you remember? It was up here on top. It was f of a, right up here. It's 6. So y minus 6 equals the slope you just worked so hard over here to find, negative 8 x minus, what was the x value that we plugged in? Go back to the top if you need it. Right up here, negative 1. Okay, I like those negatives so we can maybe get rid of that. Final answer here, friends, y minus 6 equals negative 8 times x plus 1. Final answer. And there you go. That is the equation of the tangent line at the point P, negative 1, 6. It'd be really cool to graph this on Desmos and see just how cool that is because it actually works. And we would really, really draw a tangent line at that point. Well done. All right, let's see where we left off here. So that leads us to a really important question, guys. You've learned two formulas now, right? You've done the secant formula, this one, with the limit as x approaches a. That was the first one we learned, right? Because this looked like the secant slope formula, and we're finding the limit of it. Or this new improved one as h goes to 0 of f of a plus h minus f of a over h. Which one's better? You know, they're both really, really good. I'll say right now as an AP teacher, we will tend to use this one about 95% of the time, and this one over here only about 5% of the time. But sometimes when you plug it in, you'll see that one is actually a little bit easier to use than the other. For example, here, if I was going to take this equation and try to use this formula, it would be a little bit tough, and it's because of this friend right here. Because if you think about it, when I plug in f of a plus h, that term is going to be a plus h cubed, which means you're going to have to multiply that out so many times, and that gets exhausting. When we get to the shortcut, it's going to be a lot easier. We're all going to be so happy and dancing on the streets. But for now, it's hard. So sometimes one formula is better than the other. But I would say for now, we're not going to do the ones that are really, really tricky like this until we have the shortcut, because it's going to be easier for the AP exam. So again, if you're happy, I'm skipping over this problem. So it takes me back to velocity for a second. We started out with the whole idea of average velocity and using all the average velocities to find instantaneous. So let me go back a sec. Before we talk about velocity, can we talk about your position? Now there's two ways of drawing a position graph here, folks. We can say if this is my sort of one-dimensional graph, this is just position. S stands for position. And as time goes by, at certain time periods, we have certain points on the graph. For example, at time equals a seconds or a minutes or a hours, I'm right there. That's my S position. But maybe, h time later, when I'm at a plus h, that's my position over there. So this sort of one-dimensional graph only gives you little points here and there if my position's here, my position's here. So at time equals a, my y value, I guess you would say, your position value would be f of a. And at time equals a plus h, your position or y value would be f of a plus h, right? So again, here would be your change in y's and your change in sort of x's would still be h from before. So we could still use our formula. Now, an even more visual way of seeing this would be a two-dimensional graph. Maybe this is easier because now you can see actual time has its own axis on the x, and position has its own value of y here on its own axis. So now, doesn't this look like our old graph, right? Here's our equation in black. Here's our point P that we're trying to find the instantaneous or the tangent slope. And here's our corresponding a's and a's plus h's. Here's our y values. We can use our secant slope formula here. But why would we use secant? To go back to average. Remember, it's average rate of change or average velocity. Anytime you hear the word average, you're still thinking the secant slope, the regular change in y over change in x. Okay? But here's the big deal, right? Okay, burn this into your brain. When you find the rate of change, not the average, but the instantaneous rate of change of position, that is velocity. If you think about it, you're asking yourself, how fast are you changing your position to go from there to over there? How fast are you changing your position? That's your speed, or more importantly, your velocity. So when we ask for velocity, we're asking for the instantaneous rate of change of your position. Okay, so if we go back to the old one, average is your just the secant slope, change in y over change in x. How do I know that's not instantaneous? Because there's no limit on there, right? There's no lim. If there was a limit, then you're thinking about the tangent slope, the instantaneous slope. So average is still always the secant formula. For instantaneous, look what we did. Let's attach our limit on there of the secant slope formula. Okay? Notice our notation over here. This means the velocity at time equals a is the limit of our new secant slope formula. Okay, again, we see this one a little bit more than the older one that we showed before, the f of x minus f of a. Okay, so for today, just know that instantaneous is the same thing as the tangent slope as well. Okay, maybe we get a little chance just to try one, and then we'll continue this in another video. All right, here we go, a typical physics problem. You throw a ball in the air, there's your velocity. Your height in feet after t seconds, there's your sort of x values, is given by this formula down here. So h is height, t is time, that's basically your x values. Question for you, friends, can you find the velocity when t equals 2? Now, I just said velocity. If I said average, if I ever say average, then you're going to go back and do the secant formula, secant slope formula. But does it say average? No, no, no. So if you don't see that, assume we mean instantaneous, which means we want to use our new formula with the limit. Okay? Average means you're going to go back to the old secant way. If you don't see that, we mean instantaneous, and we're going to use the new formula. Okay? So this formula here with y is the position function, because it's height in terms of time. We want to find the velocity, which is the change in position. And so we're going to use this formula with the limit attached. Okay? In the next video, I'm going to start here and try to use this new formula and try to find the velocity when time equals 2. But good start today on this big chunky section, and I'll see you in the next video.